Welcome, ladies and gentlemen, to the first webinar of the OASIS project. My name is Christian Simon. I will be speaking on behalf of Kai Reinecke, who unfortunately could not be here today. But I hope to being able to provide you with as much detail as Kai Reinecke could. And in the end of the presentation, there will be his email address and also my email address if there will be some questions concerning the talk. Kai Reinecke is from the Leibniz Institute for Agricultural Engineering in Potsdam, and I will give you a short introduction to that. The Leibniz Institute for Agricultural Engineering has two main goals, which are both listed here. The first goal is to develop sustainable technologies for resource-efficient utilization of biological systems to produce food, raw materials, and energy to meet the challenges of the changing climate and global requirements. They also develop processes for sustainable land management as well as innovative technical solutions for agriculture and industry. The Institute is organized in 4 main programs, of which I will give only an example for quality and safety of food and feed, because it's it fits perfectly to the OASIS project, because one of the OASIS project's main topics is the safety of food or health in general. Down here you can see the website if you're interested in more details about the Leibniz Institute. The talk which I will be giving today is divided into 3 parts. At first I will give you a very short introduction into food preservation processes. After that I will be talking about the inactivation mechanisms of bacterial spores under pressure. And last but not least, I will give you examples of microscopic analysis of how to investigate endospores and the activation of endospores. When talking about the preservation of food, one has to be talking about bacterial endospores. Bacterial endospores are a dormant form of bacteria, and which they form when they experience situations where they don't have any nutrients, for example, or where there's not a lot of water. So in generally speaking, a situation where vegetative cell would not survive. So these bacterial endospores are more or less everywhere, and if they come in contact with, for example, a good example is always meat, because meat has a lot of water in it and a lot of proteins. So if these spores get in contact with, for example, meat, they will go back to become a vegetative cell and divide and start living again. And if you want to preserve food, one has to sterilize these bacterial endospores. So if the preservation of food is not done the right way, then it can cause foodborne diseases. As for this example, on the left side you see a funeral of a family which home canned string beans in Albany, Oregon, and they didn't do it the right way. So the bacteria survived, and in this case the bacterium Clostridium botulinum, which causes botulism, and these bacteria produce a paralyzing toxin which can kill people or which causes foodborne disease. There's more examples of bacteria which cause harm to humans or to animals, but I will be only wanted to show you one example. So it has to be done the right way. So on the next page I will show you different methods to preserve food. This slide shows pasteurization and sterilization methods. On the left side you can see different categories: mechanical, thermal, isostatic high pressure, and so on. I will be only talking about the isostatic high pressure treatment, but for example, thermal treatment is very well known. It's done with milk, for example, and it's you can find thermally treated products in the supermarket. It's different for isostatic high pressure treated products because some mechanisms are not yet known, especially concerning the inactivation of bacterial endospores. So I will be talking about that a little later. Here's a short list of the features of high pressure pasteurization. I will not be talking in detail about all the bullet points of this slide, but maybe the most important ones are the last 2 of them. The high pressure minimally affects food qualities and natural properties, which is very consumer friendly. and also it inactivates microorganisms and enzymes at ambient temperatures at about maybe 37 degrees or so. And the last point is of course important for the inactivation of the bacterial endospores, which I'll be talking about in the next part of this talk. To understand the inactivation mechanisms of bacterial endospores under pressure, one of course has first to know how a spore is constructed, and then see what happens if a spore is set under pressure. This slide shows you the basic structure of a bacterial endospore. The bacterial endospore has a coat, an outer membrane, which surrounds the cortex of a spore. The cortex itself surrounds the germ cell wall and the inner membrane, and inside the spore there's the spore's core. The spore's core is very dipicolinic acid rich, and this dipicolinic acid, or the calcium ions, play a huge role in the two-step inactivation mechanism that was presented by Zetlow in 2003, which is shown on the lower side of the image. High pressure thermal sterilization has the aim of inactivating bacterial spores, and it combines pressure treatment with thermal sterilization. The two-step inactivation mechanism has two stages, of which the first stage consists of the dipicolinic acid release out of the spore's core, and the stage 2 has a lysis of the cortex. And with of course there's more detail to that, of course, to the whole process, but what we try to do with the microscopic images or the analysis I will be showing you a little later or in the next slides was to see the different stages of this inactivation mechanism. In the next few slides I will be presenting microscopic analysis to investigate endospore inactivation under pressure, and unfortunately I'm not able to tell you about the other methods that were carried out by Kai Reinecke and his colleagues. Of course, at first they try to build a model, and they used plate count, high performance liquid chromatography, GMO, and afterwards they used flow cytometry and different microscopy methods to correlate that with the model, and also to do a verification for that model. And today I will be only talking about the microscopy part. I will be talking about focused ion beam experiments that Kai Reinecke carried out, and also I will be talking about X-ray microscopy investigations that Kai Reinecke carried out. A focused ion beam works more or less like an electron microscope, but the focused ion beam uses gallium ions to cut through the object of interest. That's especially of use if you want to look at the inner structures of an object, as for Kai Reinecke's group, the bacterial endospores. They are interested in the inner structures of the spores, so the spores have to be cut in some way if you want to look at them with a scanning electron microscope. So as an example, on the left side you see a bacterial spore, and in front of the bacterial spore you see a rectangular hole which was cut by a focused ion beam. On the right side you see this, I don't know, it's not the same hole, but it's the same sample. It's also bacterial endospores. I think they have a platinum layer over them, and this rectangular hole was cut, and it also cut through the focused ion beam also cut through the endospores, and you can clearly see the inside of the endospores. So this technique works, but it's not very convenient. It takes a lot of time, and if an analysis method is used or necessary to look at the spores very quickly, then this method is maybe not the method of choice. This slide shows the physiological state of Bacillus subtilis spores at treated with 150 megapascal and 37 degrees Celsius. So on the lower side you see microscopy measurements. On the left side, or on the left side, you see a transmission electron microscope image where you can nicely see all the details. You see the spore's core, you see the cortex, you see the outer membrane of the spore. And Kai Reinecke wanted to see, because transmission electron microscopy preparation is very sophisticated and also takes a lot of time. Kai Reinecke wanted to see whether it's possible to look at the inner structures also with this focused ion beam sectioning. So on the right side you see also untreated spores that were cut by a focused ion beam, and if you look very closely you can also see the inner structures, but not as good, of course not as good as with a transmission electron microscope. So what I told you before, that after the high pressure and temperature treatment, the bacterial endospores release the DPA, the dipicolinic acid, from their core, and that's what you can see on the images more to the right. On the image totally to the right, you have spores that were treated with 150 megapascal for 90 minutes. And these are, they are hollow shaped, they look a little bit shriveled, which could be because they were air dried. I'm not sure about this image, maybe they were air dried, could also be that they were critical point dried. Now I'd like to show you the X-ray microscopy images that Kai Reinecke performed with his group. X-ray microscopy is a good example for OASIS, because X-ray microscopy used to be limited to synchrotron facilities, but has been transferred to the laboratory, but it's not very well known, and I think the method still needs some development in the laboratory, but still it can be used, and it can be used for real applications. So this is maybe a good example for OASIS, because maybe a biologist or people who are in food safety, they don't know X-ray microscopy because it used to be limited to synchrotron facilities. And on the other side, there's the person who is developing the method, and he doesn't have any applications. So that's where OASIS could get useful. So as you can see, with the one of the main advantages of X-ray microscopy is that the sample preparation is almost non-existent. The samples only have to be frozen, plunge frozen, and then you put them in the microscope, and you can look at the samples. Also another advantage of X-ray microscopy is that it has a very good contrast a very good contrast for hydrated samples. And the spores they're not very hydrated, they're less hydrated than a vegetative cell, but as you can see on the images, you can also see the inner structures of the spore. I don't want to go into detail, but you can see that the inner structures, that it's possible to see the inner structures, and that was maybe the most important thing that came out of the investigations, because as you can imagine, the focused ion beam slicing is a lot more time consuming than just plunge freezing the cells and look at them instantly. So this is already the last slide. There are some open questions, of course, some research demand. Maybe the most important point of the research demand is the spore tomography of individual spores. I didn't say that on the previous slide, but X-ray microscopy has a high penetration depth through samples, so it's possible to look at a whole sample, at a whole spore, maybe a whole cell also, at different angles, and reconstruct a tomography out of that. And that's very interesting for the spores, of course, because if you could, as a tomography, you have a volume where you can just put in layers of interest, like slicing, but digitally. So this would be very interesting for the spores. Apart from that, there's of course more detailed questions concerning the structure of the spore, what happens when spores are pressure treated, but I will not go into detail with that. So I'd like to thank you for your attention. If there are any open questions, and I'm sure there is, you could write an email to Kai Reinecke, which is the email address above, or to me, which is the email address below. Thank you for your attention.